Welcome to the deep dive. Today we're tackling, well, a really tricky problem in the AI world. Accountability for these big language models.
Yeah, specifically, how do you prove where some text actually came from? Especially when you're dealing with closed models, the GPT-4s, the Claude 3s.
Right, the ones hidden behind APIs. You can use them, but you can't see inside.
Exactly, it's a huge forensic challenge. If one of these models generates something problematic, or maybe just needs proper credit,
Yeah.
how do we know it was that specific model?
And the usual methods like watermarking, they're okay, but
They're opt-in. The company has to decide to put them in. And they often need specific ways of generating the text. It's not inherent.
which brings us to today's sources. They reveal something pretty wild. These models might already be, in a way, signing their own work.
Not intentionally, not through code someone wrote for that purpose, but because of the math itself. There's a geometric constraint that just happens.
And it's apparently almost impossible to fake. So our mission for this deep dive is to unpack this hidden signature. The idea that every language model's output naturally sits on a unique, high-dimensional ellipse, a hyperellipsoid.
And this isn't just theory. It falls right out of how these models are built. It acts like a built-in forgery-resistant check, a shortcut to knowing the source.
Okay, let's get into it.
Oh.
How on earth does complex geometry like an ellipse just emerge from processing language?
Right, so it boils down to the very last step the model takes before giving you an answer. Pretty much all modern LMs use a final normalization layer. Think RMS norm, layer norm.
Yeah, those are standard components for performance, right?
Exactly. And what that layer does, essentially, is it takes the model's internal thinking, the hidden state, and squishes it onto the surface of a high-dimensional sphere.
Okay, so imagine this internal state, like, mapped onto a giant invisible ball.
Precisely. A ball in maybe, 4,000 dimensions or more.
Yeah.
Now, that state, sitting on the sphere, needs to be turned into probabilities for the next word.
And that's the final projection layer.
Yes, the final layer. It's a linear transformation, basically multiplying by a big matrix, the unembedding matrix, often called W.
And what does multiplying do to our sphere?
Well, a linear transformation stretches and rotates things.
Mm.
And if you stretch and rotate a sphere,
You get an ellipse. Or I guess a hyperellipsoid in many dimensions.
exactly that. And the model's final output, the log probabilities or log probs it gives you for each possible next word.
Those are the confidence scores for what word comes next.
Right. Those log probs, after centering, are forced to lie exactly on the surface of that specific hyperellipsoid. And since every model has its own unique final W matrix,
Each model gets its own unique ellipse signature. Why?
that's the core idea. So to verify, you take an output, get its log probs, and just check the distance. Is it on model A's specific ellipse?
If yes, verified. If it's off, even by a tiny bit.
Then it almost certainly didn't come from model A. The sources show this is incredibly sensitive. It can tell apart different checkpoints of the same model training run.
Like OMO 2 version 1 versus OMO 2 version 3.
Yeah, the geometry is that distinct. The distance check is stark.
Okay, this feels different from other methods. You mentioned watermarking. Why does this ellipse thing fill a new niche? What makes it special?
Well, the sources highlight 4 key properties. First, and maybe most surprisingly, it's naturally occurring.
Meaning nobody has to remember to code it in.
Right. It just happens because everyone's using these final normalization layers for, stability and performance anyway. It's a side effect of good engineering.
An inherent property, not an add-on. Okay, what's second?
Second, it's self-contained. This is huge for practical use. To check an output, you don't need the original prompt. You don't need the whole massive model file.
What do you need?
Just the parameters that define that final ellipse. Basically, the W matrix and maybe some bias terms. That's it.
So a company could share just the ellipse info with an auditor without giving away the secret sauce of the entire model.
Exactly. It solves that intellectual property headache. Third property, it's compact and redundant, meaning the signature is there in every single token the model generates. You don't need a long text sample to find it. One output, one set of log probs is enough to check against the ellipse.
One-step verification. That's fast. Opens up possibilities for real-time checks.
But the fourth property is arguably the most important, forgery resistance.
The security aspect. Why is it so hard to fake? If I can query the model and see outputs, can't I just figure out the ellipse myself?
That's the crux. Unlike simpler signatures you might be able to guess or copy, faking this specific geometric constraint, this hyperellipsoid, without the original parameters is, well, it's computationally infeasible.
Okay, let's dig into why it's infeasible. What would an attacker have to do?
Okay, so the only real attack vector is to try and steal the ellipse parameters. First, you need to get a ton of logprob outputs from the target model's API
Querying it over and over.
and over. Then you try to mathematically fit an ellipse to all those data points you collected.
How many data points are we talking?
Well, the math tells us the number of samples needed scales quadratically with the model's hidden dimension size, d. So roughly would or do samples.
And D for these models is big.
Oh, yeah. Even for a small open source model like Pythia 70-meter, d is 512. That means you need over 130,000 outputs.
130,000 queries.
Yeah.
Okay. What about something like Llama 3.8b?
For Llama 3.8d is 4096. You'd need over 8 million outputs.
8 million API calls just to get the data. That's got to be expensive.
Extremely expensive. The actual cost, considering the whole process, seems to scale even faster, maybe supercubically. Let's put dollars on it. For the smallest commercial model, Babbage 002, the sources estimate over $1,000 just for the data extraction.
Okay.
Now scale that up. For something like GPT 3.5 Turbo, where D is maybe around 4,600, the cost estimate blows up to over $150,000.
Wow. $150,000. That's a serious barrier for most, but maybe not for, say, a nation state or a huge competitor. Is the cost the only protection?
That's a fair point. And no, it's not just the cost.
Yeah.
That's just step one of getting the data. Step two is where the real lock is, the computation.
Actually fitting the ellipse to those millions of data points.
Right. And that fitting process is incredibly computationally heavy. The time complexity is estimated at $1D.
Okay, LD6 sounds much worse than LD dollars. What does that mean in practice?
It means the difficulty explodes incredibly fast as models get bigger. Like if you double the hidden size D, the work required doesn't just double or quadruple. It multiplies by $266, which is 64 times.
So a slightly bigger model becomes vastly harder to attack.
Vastly harder. The required computation time just skyrockets. The sources did some extrapolation. For a typical large model, like a 70 billion parameter scale model, trying to compute the ellipse parameters from the data, even if you had the data, would take thousands of years on current hardware.
Thousands of years. Okay, so it's not just expensive, it's practically impossible from a time perspective, too.
Exactly. It's effectively a trapdoor function.
Okay.
Easy to check if you have the key, the ellipse parameters. Nearly impossible to reverse engineer or forge without it.
That really does change the game for proving where AI text came from. So how can we use this? What's the proposed system?
The sources outline what they call an output verification protocol, and it functions very much like a standard cryptographic tool, a symmetric key message authentication code, or MAC.
Okay, break down that analogy for us. How does it map?
So think of the model's ellipse parameters, that W matrix and the biases, as the secret key. Only the model owner or someone they share it with has this key.
Got it. Key ellipse parameter.
Then the model's output, the log probs it generates for the next word, contains both the message, which is the actual probability distribution, and the tag.
Where's the tag?
The tag is encoded implicitly in the output's geometric position. The fact that the logprob vector lies precisely on that secret ellipse surface is the tag.
Ah, so the position acts as the authentication tag.
Correct. And the verification is then super simple. Anyone with the secret key, the ellipse parameters, can instantly check if a given logprob output actually lies on the ellipse. If it does, the tag is valid, the message is authentic. If not, it's a forgery or from a different source.
This seems incredibly powerful for regulation and just general trust.
Absolutely. Imagine a scenario where, say, regulators require AI providers to register their model's ellipse key with a trusted third party. They don't give away the whole model, just the key.
Okay.
Then, if some harmful or disputed text appears online, that third party can take the text, get the log probs, and use the key to check. Did this actually come from model provider X's specific system?
And they can prove it forensically without needing the provider's cooperation at that moment and without exposing the provider's core IP.
Precisely. It enables accountability in a way that respects proprietary concerns. It's a mechanism for proof of origin we just haven't had for these closed models.
Naturally occurring, requires only partial info sharing, single-step verification, and computationally infeasible to fake. That really is something.
It provides a strong layer of attribution.
This has been, absolutely fascinating, tracing this hidden geometry, but like any system, it must have limitations. What's the catch here?
The main vulnerability is that the signature, while hard to forge, is relatively easy to erase.
How so?
If someone takes the model's output and just slightly tweaks the words, maybe even just the underlying log probs if they have access, the point is no longer on that precise ellipse. the signature is broken.
Or if they could modify the model's final layer weights before releasing it.
Same effect. Change the weights, you change the ellipse. The signature is specific to the exact parameters. So it's great for verifying unmodified output from a known model state, but it's not tamper-proof after the fact.
So if true, lasting accountability needs something indelible, something you can't just wipe away. Where does that leave us?
Well, that points to the next big research question, doesn't it? We found this amazing geometric constraint, this polynomial relationship just hiding in plain sight in standard architectures. What else might be hiding there?
Are there potentially even stronger mathematical constraints baked into these networks?
Maybe. Could there be constraints that are fundamentally harder to remove? Maybe something non-polynomial, offering guarantees closer to true cryptography? That's what researchers need to look for now, mathematical structures within these LMs that could provide unerasable proof of origin. The geometry might hold even deeper secrets.
The idea that the path to truly robust AI accountability might lie hidden in mathematical structures we haven't even discovered yet. It's definitely something to think about. Thank you for joining us for the deep dive.